First, everyone, welcome to the second lecture of the session this morning in this room. The speaker is Cosme Louart. He is currently an assistant professor at Chinese University of Hong Kong at Shenzhen. Today, he will talk about concentration inequalities. Okay, please.
Okay. Thank you, everybody, for attending this session. Yes, I'm very honored to be here. Just let me say some word of context before presenting the content of my talk. So when I started my PhD some years ago, my goal was to study the performances of some simple machine learning algorithm. And we used to use some random matrix theory tools to design the estimators. And then we had two issues. Most of those random matrix tools were starting from Gaussian hypothesis, which was highly unrealistic. And the second issue was that we were studying more and more complex algorithms, and then the Gaussian tools we were using were too laborious, so we needed some new tools to study this kind of algorithms. And that's when I come upon the concentration of measure theory that I will talk about today. I think that it's underused by statisticians, and I will present today some tools to set some efficient concentration inequalities. So I titled my talk "Operation with Concentration Inequalities" because that's mainly what we will be doing. Just to present it in a simple way, if you have some random variables x and y, and you assume that you have some concentration properties on x and y, then it is well known by statisticians that you can set the concentration of x plus y. Usually they study quantile function, but here I will just express the concentration with an operation called the parallel sum of alpha and beta. I introduce later this parallel sum. Why do I do that? It's because it will give me some scheme to treat this kind of concentration inequalities. And when it will get more complex, then this kind of operation will prove its efficiency. The same thing will happen if you want to compute the product. Then what will appear is the parallel product of alpha and beta, where alpha and beta are the concentration function of x and y. So for random variables, it's very easy to get. It's more interesting when we treat random vectors. And for that, we need a specific assumption on the random vector. So the operation will now be mapping phi that will go from from a vector space to R. Okay, so the hypothesis I will do on my random vector will be taken from the concentration of measure theory. So for those who don't know, this inequality is true, for instance, for Gaussian vector and for some specific alpha. So that there are several ways to set this kind of inequalities. And we will see later that it concerns a lot of random vectors. So it's powerful in the sense that it's true for any one-Lipschitz mapping F. So to set the concentration of a random vector X, actually, we make an hypothesis on a random variable that will be f of x for any f1 Lipschitz. If we have the concentration of x, and then if we have a certain mapping lambda that will take some real values, and that will follow this kind of concentration inequality, where this lambda of z will be controlling the variation of my phi of x. So the goal is to set the concentration of phi of x, and it's possible under this assumption. And then we see appearing again the parallel product. So that's why I first presented the results for random variables, is because at the end it's the same thing that happens for random vectors. Okay, so what we have, we start from a concentration of measure hypothesis on x, then we assume the concentration of the variation of the phi of x. So that could be the estimator, for instance, if you study a machine learning problem. And then you can set the concentration of your estimator. So that allows you to give some guarantees for your algorithm. So that's why all this was useful for what I was studying. I will mainly speak about theoretical results today, with very few practical consequences. So my presentation will be quite didactic. I try to do some animation so that the proof will be easy to understand. If you have any question, you can interrupt me. I think that I have more time than needed. And then I will study a simple application of this result with the Hansen-Wright inequality, which is very used in a random matrix theory. So it's the same inequality where you replace your phi of x with x transpose ax. So here you have mainly the content of my talk. First, I'll give some motivation. Actually, I skipped the motivation, but if you have some question, I will present it at the end. So I will start with the Hansen-Wright inequality just to show you the goal, present you the goal, sorry. Then I will study the parallel sum and parallel product for random variable. And then in the third part, I will extend it to random vectors. So we will try to set concentration inequality in high dimension. Then I'll apply it to Hansen-Wright inequality. And then in the last part, so I will set something that is now called as the multi-level concentration. It has been set by several authors, and I try to present another way to set this kind of inequalities. So you will see that it will be a simple development of what will be done in the previous subsection. Okay, so sorry, I skipped the motivation from random matrix theory because it's a bit out of the subject, I think. I want to have enough time for the proofs. So the goal, one of the goals, sorry, is to set the Hansen-Wright inequality. It dates back from the 70s, and it sets that given a deterministic matrix A and a random vector Z with independent entries, Z1 to Zn, that satisfy a kind of sub-Gaussian hypothesis, then I can set the concentration of this quadratic form around its expectation with this concentration function where we see, yes, some constant appearing that do not depend on n. And we have two regimes. So there's one regime that would control the tail of the distribution of Z transpose AZ, and another one which will control the head and also the order of the first moments. And we have two speeds. The first one is the Frobenius norm of A, and the second one is the spectral norm of A. Then an improvement was provided by Adam Zak in 2014. I think that was the best result that was obtained. So the concentration is a bit the same, but the hypothesis is different. You don't need anymore to assume the independence between the entries of Z, but you need this concentration of measure hypothesis. So that's true, for instance, if Z is uniformly distributed on a sphere of radius square root of n, or if Z is a canonical Gaussian vector, or if it's uniformly distributed on the ball. And if you have any such, yes, and many others that I will present later. And also you need a bounding assumption on the expectation of Z, and then you have exactly the same concentration inequality. And to set this result, I will just, first set the concentration of a general phi of Z with some hypothesis. Apply this concentration on phi to a phi equal to Z transpose AZ. Then we see that this mapping can be controlled by the spectral norm of AZ and spectral norm of AZ prime. So that's the scheme of my proof. The last thing I wanted to say, sorry, I forgot. Okay, but so let's go on. So now we will first study random variables, so variables in R, and we see where this parallel sum that I defined this way here appears. So here I define it for invertible mapping A, alpha, and beta, but you could use the Clartard inverse to generalize it to any increasing or decreasing mapping alpha and beta. They must be similar at the same time. They must be increasing at the same time or decreasing at the same time. Okay, so just a scheme to present what's the parallel sum. If you have two mapping alpha and beta presented on this graph, and you want to compute the sum of those two mapping, it's easy. You just sum the two curves. And the parallel sum is exactly the same thing, but instead of summing on the y-axis, you will sum them on the x-axis. It's because the inverse is just the symmetric through the line y equal to x. Okay, and then we have this result. So if you have the concentration on x and concentration on y, then you deduce the concentration on x plus y, with the parallel sum. It's proven in 3 lines. So you will denote gamma, the parallel sum of alpha and beta. Then, by definition of this gamma, since it's the inverse of this function, if you apply this function to gamma, then you recover t. So you have this identity. And then you replace the t by its value here. So you then have to bound the probability that x plus y is bigger than this sum. And you know that it's lower than the probability that x is bigger than the first one, plus the probability that y is bigger than the second term. And then you apply just the hypothesis on x and y, and you get alpha of alpha minus 1 of gamma. So it's exactly gamma of t, and the same for y. So that's how. No independence. But I think it was known, but in another way, when they instead of expressing the result with the concentration function alpha and beta, they do it with the quantile function, which is exactly the inverse of alpha, if you have an equality here. So it's just another way of expressing it, but then it's powerful afterwards. So just to give an example to say why we need this constant 2 here. So I give an example where for some t, actually I have an equality here. So let's consider the uniform distribution on those 3 triangles. So it's a distribution on R2, and the probability of xy is defined just equal to 1 over the total area if it belongs to this, and otherwise it's 0. Yes, so if you compute, just a little hint, if you compute the parallel sum of alpha and alpha, it will give you, applying this formula, it will give you alpha of t over 2. Now, if I want to compute the probability that x plus y is bigger than t, so it's everything that is over this line, it's exactly the area of this plus the area of this over the area of the 3 triangles, so it's 2 over 3. And it's exactly equal to the probability that x is bigger than t over 2. So t over 2 is here, and then I just have one triangle that is over, plus the probability that y is over t over 2. And this is equal to alpha of t over 2. So it's equal to the parallel sum of alpha and alpha. Yes, that's it. So we cover 2 times the parallel sum exactly here. So it means that in this case, the inequality is an equality. So that's why we require this 2. Okay, and it's true for other t. Okay, let's see now what it is for the product. It's the same thing, actually. So we define the product as the inverse of the product of the inverse. But yes, we want this mapping, this operation to be stable with increasing mapping or stable with decreasing mapping. So we require that alpha minus 1 and beta minus 1 are bigger than 0. So you need some precision to define well this mapping, but we don't care about that. Because I just want to give you the general spirit. And we have exactly the same result. So if you assume that the x has this concentration, y has this concentration, then x times y has the same concentration. And it's just because of the fact that if I set gamma equal to the parallel product, then I have this inequality. Yes, and I just replaced the t again with the product of alpha minus 1 and beta minus 1, and then it's the same thing. I divide my probability in two pieces to get at the end 2 gamma of t. Okay, so same thing for parallel sum and parallel product. And now I will still work with random variables, and I will try to give the general idea that let appear those two regimes in Hansen-Wright and actually we can already see it in dimension 1. So no need to have a high dimension to see those two regimes. So I will do this assumption on X. So yes, I will assume that X is concentrated around an independent copy with the concentration function alpha, and then I want to set the concentration of XAX. It's in dimension 1, so actually it's equal to AX squared, but just I represent it in the same way as Hansen-Wright with a quadratic form. So so I say that my vector, I say that I have a concentration inequality on some variable if it's concentrated around an independent copy X prime, sorry. So I try to bound this difference where I have an X prime here. So I try to bound AX squared minus AX prime squared. Yes, with a simple plus and minus, I let appear this AX X prime, and then I can bound it. Since I have X minus X prime, I can factorize by X minus X prime to obtain this inequality. And I will call this new random variable V. As a consequence, if I know that V satisfies a certain concentration inequality beta, from the previous slide, I can set the concentration of AX squared minus AX prime squared. It will be the parallel product of alpha, the concentration function of this, and beta, the concentration function of this. So I have two questions. What is the good choice for beta, and what is alpha parallel product with beta? Okay, so to choose well beta, it will depend actually on alpha, because V, as we see, is depending on X, so we can use the concentration on X to deduce the concentration function on V. Okay, so it's the sum of two independent vectors, so the probability that it's bigger than t actually is lower than 2 times the probability that one of them is bigger than t over 2. Then, I will try to use the median of this AX as a pivot for the concentration. So I just remove M from one side and remove it also from the right side. And then there's a way that I don't describe it here to relate the concentration around the median with the concentration around an independent copy. And that gives me this new inequality. Then I'm getting closer to the hypothesis I had on X. Actually, it's exactly it, but just with A in front. And I have this concentration inequality that is only useful when T is bigger than the absolute norm of M. Absolute value of M, sorry. Just to be more precise, I introduced an increment function, so it will be useful later. So please remember how it's defined. It's very simple. It's indexed with a U, and you say that if t is lower than u, then it's equal to 0, and if t is bigger than u, then it's equal to plus infinity. So then I can rewrite this mapping as the minimum between the increment function on M, because if t is lower than M, then the bound is useless. And if t is bigger than M, I copied again what was inside alpha. And then, yes, I'm not very happy here because I have M appearing on both sides, and actually I can remove one of them because I know that so I will just go a bit further than M. I will go to 2M, and then I can use this little trick. I know that if t is bigger than 2M, then t over 2 is lower than t minus M. And since alpha is decreasing, I can replace then t minus M over A by t over 2A. And that's the final inequality I get, and that will be the beta I will choose. So I have my beta that depends on alpha, and then now I want to deduce what is alpha times beta. So that's the second question. I just recopied the value of beta. So I want to compute this parallel product, and then we will use some some important tools with a parallel product. Is that unlike the classical product that will distribute on the right, the parallel product will distribute on the left. So we can show that the alpha can be taken out of the operation. Let's follow the step. So if you compute the alpha composed with F parallel product with G, you can let the alpha enter the inverse, like this. And then you recognize here the inverse of alpha composed with F, product alpha composed with G. That's exactly the parallel product of alpha composed with F and alpha composed with G. So we can take the alpha out of the parallel product. That's what I do here. And then we need to compute the parallel product of the identity and a minimum. So I need to compute the inverse of a minimum. It's a simple fact that it's the maximum of the inverse. Everything works for functions that have the same monotonicity. Okay, so just a simple graph to make you understand why I have this identity. If I have two mapping F and G, the minimum would be this mapping in green, and then the inverse would be the image through the axis y equal to x. I obtain those mapping, and the maximum and the inverse is exactly the maximum of the two inverse. I also need to compute the inverse of the increment. So it's not inversible, but I will use I use actually the Clarta inverse. I don't define it, but you can just see that you can just imagine that it's the symmetric towards the axis y equal to x. So it's done here, and I see that the inverse of the increment is just the mapping equal to u on r plus and minus infinity on the rest. So I have, with those simple tools, then I can pursue the inequality. So it's inverse of this. I just recopied the definition. Inverse of identity is identity. Inverse of minimum is maximum of the inverse. Then I recopied the inverse of the increment. And here the inverse of identity over 2a, sorry. And at the end, I have this. Okay, I let identity enter the two entries of the maximum. And again, I have to compute the inverse of a maximum. It's a minimum. And here I see appearing, so it's identity over 2m, and here I have a square root. So it makes us remember of the Hansen-Wright inequality. It's exactly Hansen-Wright if instead of a general alpha, you will have this mapping, e to the power minus t squared. And then I would retrieve Hansen-Wright. So the conclusion of this slide is that even with random variable, we can already understand where those two regimes comes from. It's because at the beginning, you had an inequality on V around its median, and then you transformed it to control on the tail on V with this increment function that afterwards, when you do the parallel product, will let appear two regimes. A first one, which is just a factor of the identity, and the second one that let appear a square root. Okay, so we'll see later why how Hansen-Wright is setted with M that will be the Frobenius norm of A, and little a will be the spectral norm of A. Okay, so now we are ready to set results in a higher dimension. For that, I give you some words about concentration of matter theory for those who are not familiar with it. For that, I take the historical example of Levy that was on the uniform distribution on a sphere of radius square root of n. Yes, sorry, I should have put the square root of n here. So I drew schematically some drawings on this sphere. So we are in dimension n. So the picture is on dimension 2, but you can imagine that it's random drawings on the sphere. And then I look at some images of these drawings through two mappings. The first one is just a normalized sum. And the second one is the infinite norm of Z, so the maximum of the absolute norm of all the entries. And what we see, if you do it with a simple solver, simple code, you will see that you will create two random variables that will have in common that the standard deviation would stay the same even if you let n increase. So in that case, we say that it's of order 1, meaning that the standard deviation of those two random variables is independent with n. So it's strange because it's really different random variable, and Z is belonging to a manifold of increasing diameter. And what happens is exactly the concentration of measure phenomenon. You start with what could be called a distribution diameter of order square root of n, and you end up with what is called an observation diameter, so the diameter of the observation that is of order 1. An observation here is this kind of functionals, and what we see is that they have in common that they are both 1 Lipschitz for the Euclidean norm. So actually, any such 1 Lipschitz functional will create a random variable with a standard deviation of order 1. Okay, so this phenomenon was later studied by Millman in the 70s, and it was stated this well-known result on the concentration of a Gaussian vector. So it could be concentrated, the mean of the Gaussian vector has no importance. The only important thing is that the covariance has a bounded spectral norm. And then we have the concentration of any 1 Lipschitz mapping of Z with this Gaussian tail, this Gaussian decrease, sorry. And Z prime is an independent copy of Z. Why this inequality is very powerful? First, because it's independent on n, on the decrease, so independent on the dimension, and it's true for any 1 Lipschitz mapping F. And once we have such a random vector, here it is the Gaussian random vector, then we can deduce a lot of other vectors that would satisfy the same inequality. Indeed, if you consider mapping phi, so it's a transformation in Rn, then the phi of Z will also be a random vector. And we just assume that phi is lambda Lipschitz. Then we can set the same inequality, but for phi of Z replacing Z. It's very simple. You just divide both sides by lambda in order to get here a 1 Lipschitz mapping. Then you can use the hypothesis on Z, and you obtain directly the bound, which is a Gaussian decay with speed in lambda, in order lambda. Yes, just some words. Once we know this, we see that we can consider a lot of a wide range of such random vectors. In particular, we can consider random vectors that don't have independent entries. That's very important in machine learning in general, I think, because then it looks like a more realistic hypothesis we can do on the data, because you don't need anymore to assume that the data is Gaussian. You just need to assume that it's a phi of a Gaussian vector. And actually, plenty of distribution could be defined like this. In particular, all the images that are constructed with GANs are simple Lipschitz mappings of a Gaussian vector. So the images, the distribution of the images that are constructed through GANs can be seen as a random vector satisfying this inequality. There's another very important result in concentration of measure theory, which is a bit more constrained, but it concerns other types of random vectors. It's more a combinatorial result, where the first one is more geometrical. It's owned to Talagram, and it says that you have the same concentration inequality for only 1 Lipschitz and convex mapping, so that's why it's more restrictive. But it's true for any random vector with independent and bounded entries. Here, if you start from a vector Z that is Gaussianly concentrated, this is a Gaussian vector, then any phi of Z cannot have any atoms because phi needs to be lambda Lipschitz. But in this case, you just assume that it's bounded, so you can consider vectors that have some atoms in their distribution. So that's why it's a complementary result. Later on, we will prove our result with both hypotheses, this one or this one, for any one Lipschitz and convex observation F. Okay, yes. So we had this result for Gaussian vector. And then the question is, can we still deduce this kind of concentration inequality if we no longer assume that phi is lambda Lipschitz, but still we can bound the variation thanks to a random variable lambda that will satisfy some concentration inequality? And the answer is yes. That's what will be set in this slide. Okay, so I assume I have a random vector that satisfies this concentration of measure assumption with a general alpha. So before it was just with Gaussian decrease, but we'll see later how to construct inequality with general alpha. So it could be heavy-tailed. That's the important part of my talk. We will set heavy-tailed concentration inequality. Although before, most of the time, it was done with exponential decay. So the variation will be defined through a mapping lambda that will go from Rn to R plus and satisfy some concentration inequality like this one. And then I assume that the variation of phi of z minus an independent copy will be bounded by the maximum of lambda z and lambda z prime times the difference of z and z prime. Then I can set the concentration of phi of z. I can set a concentration of measure result on phi of z. So the new vector that I constructed, yes, phi is taking value in Rn. So it's a random vector, and I have the concentration function that is the parallel product of alpha and beta. Let's prove it. It can be done quite fast also. So I denote, for simplicity, lambda of z and lambda of z prime. And then again, I introduced gamma that will be the parallel product of alpha and beta. Yes, and theta will be my threshold. So if you remember in the proof of the the concentration, the product of concentration inequality, yes, the beta minus 1 of gamma was a period also. So to be simpler below, I use this notation. And then I decompose, I want to bound this probability, and I decompose it in two parts. The first one, when I assume that the maximum of lambda and lambda pi is lower than my threshold, and the second part when it's bigger than the threshold. Yes, I didn't recopy this, but it could be put, actually, it's lower than this probability. Okay, so this term is easy to bound thanks to this hypothesis on lambda z. Sorry, there should be a 2 here, because it's the probability that the maximum is bigger than theta. So it's lower than 2 times the probabilities, and one of them is bigger than theta. And then it's just beta of t, and t here is the theta, that is beta minus 1 of gamma t. So again, I have beta of beta minus 1 of gamma t. We know that we can bound it with gamma of t. What is more difficult to study is this inequality. So I will write it as a difference of two mapping h. And the idea is that I will introduce h that would be an extension of this mapping, f of phi, that would be Lipschitz, theta Lipschitz. Because my issue is that I didn't assume that phi was Lipschitz. I just assumed that I had this kind of control on the variation of phi of z. So what I do is that I will place myself on the event where lambda of z is lower than theta. So on this set, I know that f composed with phi is theta Lipschitz, because this is lower than theta. And on the rest of the universe, I don't know. But since I'm only trying to bound the probability on the event that it's lower than theta, then I can introduce a mapping that will be theta Lipschitz on all the universe. Here it's on all Rn, and equal to f composed with phi on this set. Yes, we will show the same result for convex concentration hypothesis later, and then you will see why it's Lipschitz on Rn. It's easy to see. It's just a triangular inequality. So why do I do that? It's because then I have something that looks like my hypothesis on Z, and then I can bound it with alpha of T. Yes, over the Lipschitz parameter of this mapping, which is theta here. I replace theta with its value. It's beta minus 1 of gamma T. So yes, maybe it's useful to show you here. Here you see when I was considering a lambda Lipschitz mapping, then at the end I had T over lambda. The Lipschitz parameter was on the denominator of theta. And that's the same thing that happens here. The Lipschitz parameter arrive on the denominator. And then yes, I use again this identity. I know that T over beta minus 1 of gamma T is equal to alpha minus 1 of gamma T. And then I can bound, so I can bound everything with gamma of T. I've proven this result. It's lower than, it should be a 3 then. But, yes, we are looking at result when the dimension goes big, so we don't care about the constant in front. And we can set the same result for convex concentration. Yes, I'm sorry. Here it should be, yes, I put it the convex here word, not on the good room. It should be here, and phi is taking value in R. And then, so I will set here a concentration on phi of Z, where phi is convex and 1 Lipschitz. And the proof is exactly the same, but in that case, you introduce this mapping. So just to go more into details, then I can show that it's, maybe, yeah, looking at the time, I think I will skip it, sorry. But you can show that this mapping is an extension, again, of F composed with phi, that is theta Lipschitz and convex, because it's a supremum of complex mapping. And theta Lipschitz, so as I said, it's just a triangular inequality on the supremum. Okay, so we have the same result for convex hypothesis. Okay, and so why is it interesting? Because can we obtain such alpha that would be heavy tail? Before the results were set with exponential decay, because the big result of concentration of measure theory are obtained for exponential decay. So if we don't have any such inequality with heavy tail, then the result is useless. Actually, we can show with this theorem that we can set, starting from a Gaussian vector, we can set a concentration of vector with heavy tail. That's the following theorem. So I assume that I have a vector that whose entries are all mappings of a Gaussian variable with a certain phi. And then I can deduce the concentration of x thanks to this theorem. First, I can bound the difference between phi of z and phi of z prime with the supremum of phi prime. And then I need to set, so I know the concentration of this z, it's given by the concentration of Gaussian vectors. And then I need to set the concentration of this supremum of phi prime. And that can be bounded in the following way. So I don't stay into detail to speak about Hansen right, but at the end I can obtain the concentration with two regimes again. The first one that will control the tail, and the second one that will control the head, and that will give the speed of the first moment. And this is a large tail concentration inequality on my vector x. So that allows me to construct vector where the alpha here is no more has no more an exponential decay, because the exponential is composed with something that can decrease very slowly, like you have here. Okay. And now we try to apply this result to a Hansen-Wright inequality with a heavy-tailed assumption. Okay, so I rewrote the result. It was set for independent copy, Z prime, and then f of phi of Z prime. Can we replace those independent copy with expectation? That was true for exponential decay, because we know that, that there is a kind of equivalence between a concentration around an independent copy and concentration around the expectation. So that can be shown. It will depend on some constant. But as I said, we are trying to set the result for high dimension, so we don't care about these constants. Then the same result can be set when alpha is equal to the exponential decay, can be set replacing the independent copy with the expectation. But is it true for other choices of alpha and beta? The answer is yes. You just need a further assumption on alpha. You need at least that the expectation can be defined. So we understand that we need at least this assumption is necessary. You need to be able to bound the first moment of alpha. And we can see that it's sufficient also. If you have this assumption on alpha, then you can have the same kind of equivalence. You can introduce those two constants that depend just on alpha. So that's why I assume that alpha is independent with L. Those two constants that just depend on alpha and that allows you to relate concentration around an independent copy and concentration around the expectation. So it's okay for the assumption, and then for the conclusion. So it could be the alpha parallel product with beta, but then we need the same assumption for alpha parallel product on beta to have this equivalence. For that, we take a particular beta. So that's why it was interesting to present you first what was happening for the random variables, because we know at the end that we will have two regimes. A first one, which is a factor of the identity, and the second one with the square root. So that's why we need to go an order further in order for the second regime to be also integrable. So that's the assumption on the sigma alpha that would be related to the standard deviation of f of z. And then if we have this assumption, we are able to set the concentration of f of phi of z around its expectation. Okay, and now we apply it to Hansen-Wright. In Hansen-Wright, as Adam Zak said, you can take convex concentration hypothesis. And sorry, here it's a value in R and convex for phi. Okay, and then we check the hypothesis with Hansen-Wright. So the phi of f the f of phi will be z transpose az. And then we have those two regimes. Okay, so for that we need to check first that we can bound the variation of phi of z when phi of z is equal to z transpose az. So it's done with the spectral norm. Then it's a sum. We can bound it with 2 times the maximum. And that becomes my lambda of z. And we know that, so this assumption is satisfied. Then with this lambda of z, can I satisfy this? Again, it's true because the norm of az is just an observation, a spectral norm of A Lipschitz observation of z. So I have this concentration. The second hypothesis is satisfied. And then I can set Hansen-Wright result with those two speed. Okay. And the last step is just to improve the speed of the head regime, which here is expectation of the spectral norm of AZ. Okay, I skip that. It's a simple calculus. It can be bounded with the. So if I have another hypothesis on the bound on the expectation of this, then it can be bounded with the Frobenius norm of A as expected. And we get Hanson-Wright result with a large heavy-tailed assumption on the concentration of Z. So just to compare it with Adams-Zach result, it's exactly the same, but with alpha being the Gaussian decay in the case of Adams-Zach. Okay, so now I have some minutes to speak about multi-level concentration. For that, I want to go back to the previous calculus to explain what happened. So those two regimes, they appeared because at one point we were computing the parallel product of alpha and alpha composed with the minimum of the increment and a factor of the identity. So I could take the alpha out, and then I just had to compute this thing. To find a systematic way to detail those calculuses, I introduced a new notation, more a convention. Yes, new notation and convention. First, the identity, I will just represent it in a general way. So it's strange, but we'll see later why it's useful to write the 1 equal to 1 over 1. And the speed will be the new 1. I want to write the increment in a similar way. For that, I will write it this way. So it will be a 1 over 0. So it's equal to plus infinity. And we see here that t over sigma 0 to the power plus infinity, it's equal to plus infinity if t is bigger than theta 0, and 0 if t is lower than theta 0. So that's why we use this notation. And then we want to compute this parallel product. And we have a very simple rule. What happens is that the parallel product of those two mappings is this one. And what did we do? First, we divided 1 by the sum of this one and this 0. And then on the denominator is just the product of the speed. And it's the same thing for the second term. And multi-level concentration is a concentration where you have minimum of more regimes. At least when you have 2, you have this result. Yes, and you can go further than 2. So you see that, yes, I have 2 concentration. Yes, alpha and beta, they are both defined with a minimum on a certain set A here and a certain set B here, with different exponent and speeds. And then the parallel product will be just a minimum of 1 over the sum of the exponent and t over the product of the speed. And the same thing happens when you have a lot of other, when you do the parallel product of n mappings, it's the minimum, and you again have the sum of the powers over the product of the speeds. It's very useful when you look at the concentration of n random variables. So for statisticians, it's something that we often have. We have you have concentration on some random variables, and you want to deduce the concentration on the product of those random variables. Then usually you can use this kind of operation scheme to compute the concentration of the product. When you look at random vectors, then it's when you have a phi that whose variation will be bounded with z minus the norm of z minus z prime times the product of some random variables that depend on z, and whose concentration can be expressed following it. Okay, so I just want to show this result because you see it's just 4 lines of calculus. It looks a bit difficult, but it's just 4 lines. So I want to compute I assume that all my mappings are defined as a minimum of this power of a quotient. So that's the speed, that's the exponent. So the exponent, if it's high, it means that it controls the head. If it's low, it means that it controls the tail of the distribution. And this controls the moment. The first moment are controlled by the higher exponent. So I want to compute the inverse. I just copied again. So it's the parallel product. It's the inverse of this product. So I have the inverse of an infimum, and we know that it's equal to the supremum of the inverse. So now I have a product of supremum of the inverse of this, you can compute it easily. It's just, so this equal to t means that t to the power a1 equals to the identity over sigma, and then identity equals to sigma times t to the power a1. So it's just the inverse of this mapping. You have a product of supremum, then you can just put the supremum sign in front, like this. And then you know that this supremum is the inverse of an infimum, where I inverted this mapping. And that gives me the proof. So the parallel product of all those mapping is exactly this infimum. It's on all the exponent a1 to an. So I have then this general result for the concentration of phi of z. So I assume that I have a concentration hypothesis on z. I assume that I can control the variation of phi of z with those lambda, 1 of z to lambda n of z. And then I need concentration assumption on lambda k of z. Generally, we don't directly have a concentration on the tail of lambda k of z. Generally, we have a concentration around a certain sigma 0 of k. That could be the expectation of this lambda k of z. And yes, you have the infimum. And most of the time, this lambda k of z is an image of z. So it expresses through alpha, composed with some infimum of function. But then, if you have this, you can deduce the concentration of phi of z with, as was said by the previous theorem, let appear the infimum on all the exponent ak. Just some words about this inequality. What would happen, for instance, if I have random variable lambda k? Yes, sorry. So yes, just there is a 1 here. It's because the assumption on z is a concentration with alpha of t without any infimum. So t is equal to t to the power 1 over 1, the whole over 1. So that's why we have a 1 plus something here. And then what would happen if I would have a random variable, let's say lambda 1 of z, that just compute the infimum over the singleton 0, meaning that here you would have nothing because it's infimum over a deprived of the singleton 0, but you will just have sigma 0. Yes, the probability of lambda minus sigma 0 bigger than t is lower than, so it's the infimum of everything, it's lower than alpha of composed with 0, with alpha of 0. So lower than 1. So actually you, it's more the probability that lambda k is at a distance bigger than t of sigma 0 would be equal to 0. So it means more or less that the random variable lambda 1 is a constant equal to sigma 1. So then the inequality is still robust to this constant lambda 1 because it will appear in the speed. So it will appear in the form sigma 0, but it won't affect the powers because the A1 will be equal to 0. So it means that if you have a constant appearing here, then the formula is robust, just to make you understand better the formula. So I mainly finished my talk. So this is called multi-level concentration inequalities. It appeared in some papers quite recent, one by Adamczak and Wolf. They were studying a polynomial on a random vector C. And they had this kind of inequality, so f is a polynomial, and then they had this kind of inequality where the eta f was exactly a minimum of several mappings. So you could see different speeds appearing that could be seen as the product of the sigma a1 to sigma an, and the exponent also that could be seen as the sum of the exponent. And then the same result was, not the same, but a similar result were set by Goetze, Sambale, and Sinulis. Also with yeah, the same kind of expression. To show that, so all the time it was done in an exponential setting because they were bounding the moments. And so they needed a bound on all the moments. So that's why they could not consider the heavy-tailed hypothesis. So yes, the next step is to exactly set those results in the case of a general alpha. Yes. So my final word is for statistician. I think that the simplified assumption could have that could be that could find very practical use in a lot of statistical problems. So yes, I hope you will keep this element in mind, and I thank you all for listening to me.
Okay, it's time for questions.
Yes.
Thank you, Professor, for this elegant talk. And I know nothing about this talk, and but I see that there are some notions like you are using that the concentration of high dimension. Like I'm interested in high dimension. Like why is high? Like are there so it is more difficult in high dimension or low dimension?
It's more difficult in high dimension.
So why is it more difficult?
It depends. At the end, what you want to set usually, I think, in statistics, is to set, for instance, the concentration of an estimator, and this estimator is of low dimension.
Actually,
but
like,
no, it's more. It's not a question of difficulty. It's more like no. It's for instance, we see it in machine learning. Some intuition that works in low dimension are not true in high dimension because the estimators are different. Oh. But since we need to tackle this kind of problem where the dimension of the data is big, yes, at one point you need a concentration hypothesis on your data, and this can be provided by the concentration of measure theory.
Okay.
So yes, just a word. It's high dimension, but it's true in low dimension, like this inequality. This one I was provided is true for any n, so you could use them in a low dimension.
Oh, I get some ideas, but I don't know what. But
it's like a quasi-asymptotic inequality.
Questions.
You can use it for any n.
I have other questions.
Yes.
Like, I have seen some symbols like in this. I think weird symbols. Like you have the product, like the product there is square and there is square. Yeah, square product.
Square product? You mean this?
The center? Yes, alpha square product. Beta. I think this symbol is very weird, and I believe I only see it in papers like in algebraic geometry before.
Yes. So the parallel sum is usually written with a square.
So like, is this linked to algebraic geometry?
No. Yes. People often ask this. No, there's no link with. Yes, or with free probability also.
Okay, so I know nothing about algebraic geometry, but I have seen this symbol in the paper. Like, I only see the paper. So I think I only have this question. Thank you very much.
Okay. No, for the notation, so the parallel sum, it was used by electric engineers. It was to compute the resistance of a parallel circuit of resistance. You know that it's 1 over the sum of the inverse of the resistance. So that's why they introduced it. And then it was reused in a convex analysis. Yes, to set some results on the convex conjugate of this operation. So that's why I took the same notation. I just added a plus or a time inside the square to differentiate the parallel product from the parallelity. Yes?
I had a question, like, to what extent do your results hold when your functions are only Lipschitz on average in some sense, or not
function that
like if your function f is only Lipschitz on average, or for average case x, can you guarantee some of the results?
It's not sufficient to be Lipschitz on average.
Not let's say
you need to know to know. Yes, you need to control the outliers. So that's why you need to have a concentration inequality on this Lipschitz parameter. You need this assumption. what happens for the Hansen-Wright result is that, maybe I have it here, is that the expectation of this Lipschitz parameter appears in the concentration. You see it's the M here. So it's the median, but it could work also for the expectation if alpha is integrable. So the average appears in the final concentration, but still you need to be able to control the tail. So here it comes from alpha. But for general beta, yes, it wouldn't be sufficient to know the expectation of beta.
Say you have like higher moment control, would that suffice? Like how many?
Can you speak slowly?
So if you have like higher moment control, would that suffice? Like how many moments would you need to control?
Actually, you can go further. That's what happened. So the result of Adamczak, Wolf, and also the result of Götze, they're bound. Let appear some norms. So the h to the power kf, it's L1 norm of the k derivative of f. It's because then you can use the Taylor expansion, and so you have this kind of inequality. Yes, you can bound the alpha thing. So you have the first derivative taken on x plus the second derivative taken on x, and you hope that at one time, you can go to a f as well squared taken in x, and this would be with a let's say y, where y belongs to the segment x prime, and so let's put some nodes. So this is a random variable that has some concentration that you can express, but you can express it just if at one point you can control one of the derivative. So you hope that you will have for a certain derivative d this in infinite norm. So it's the infinite, in the infinite norm, this would be bounded by a certain constant c. Once you have this, then you can deduce the concentration of the d-1 derivative up to the first derivative. It's recent result, and so I didn't put them in the talk. But then you can express the concentration of f of x. It will be a multi-level concentration close to the one of the results that are written here, with the yes, that would let appear the expectation of these random variables and the infinite norm of a big derivative. Is it clear?
Okay, there is still time for quick questions. Any other questions?
I forgot the factors. Yes. Yes.
Any other questions? Okay, let's thank the speaker again for the next talk. So it's time for lunch. Enjoy yourself.
穹苍广而横千，雾河多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为